Welcome to Biomanufacturing and Fermentation Technology. This special series unpacks execution-ready industrial fermentation challenges, one episode at a time, each focused on a real production bottleneck and its practical solution kit. From eliminating scale-up gradients to deploying real-time pattern building mini-digital twins, every episode is designed for immediate plant floor impact. If you operate from pilot to 10,000 liters and beyond, this is your execution blueprint.
Welcome back to the deep dive. I wanted to start today with a scenario that I think is going to sound painfully familiar to a lot of our listeners, specifically the bioengineers out there.
Oh, I have a feeling I know exactly where you're going with this.
It's the Sunday night scaries of the biotech world.
Yeah.
You spent months in the lab.
Right.
You have this absolutely perfect process. Your little 2-liter glass vessel is just humming. The cells are happy. The titer, the amount of product you're making is just through the roof.
Popping the champagne?
Exactly. You pop the champagne. You tell management, hey, we are ready.
And then you move to the manufacturing floor.
And then you move to the floor. You dump that beautiful process into a 5,000 or 10,000 liter tank, and suddenly the biology just revolts.
Yep.
Productivity drops, the yield is completely all over the place, and you're just left standing there trying to explain why the sure thing isn't working anymore. It's the classic scale-up paradox.
It really is the monster under the bed for fermentation scientists. And usually the explanation is just a shrug and a sigh that basically says, well, physics is hard.
Which, to be fair, physics is hard.
Very hard.
But today we're diving into a stack of sources that claim we don't actually have to just accept this as some law of nature. We are looking at a really specific solution kit.
And it's designed to be fast, right?
Super fast. Designed to be implemented in a sprint. Literally 7 to 10 days to fix this.
Which is wild because 7 days in this industry is, you blink and a week goes by. Usually process changes take months.
Right. Totally. So the mission here is really specific. It's eliminating gradients. We're talking about dissolved oxygen, DO, and pH.
The big two?
Yeah, the big two. The goal is total homogeneity, making sure that the cell at the very bottom of a 2-story tall tank is experiencing the exact same spa day as the cell at the very top.
Which really is the holy grail, because when you're dealing with 10,000 liters of fluid, you're dealing with massive hydrostatic pressure. You've got slow mixing times, gas transfer issues. It is definitely not just a bigger beaker.
No, not at all. But the payoff promise in these documents is huge. Like, we're seeing data referencing an E. coli phenylalanine case study.
Oh, the bubble column one.
Yeah, specifically in this massive 600 cubic meter bubble column setup that is basically a skyscraper of a tank.
600 cubic meters is enormous.
Enormous. And the stats, they're talking about a potential titer increase of 18 to 25%.
That is just, that's a quarter more product just by fixing the mixing.
Just the mix.
That fundamentally changes the unit economics of a product.
Exactly. And they actually reduce spatial variation across that huge vessel to less than 5%.
Wow.
Yeah. So to get there, our sources lay out this 4-pillar roadmap. We got a counterintuitive scale-down model, some really serious instrumentation upgrades, a mechanical surgery on the tank itself, and finally, these smart control loops.
It's a comprehensive overhaul, really, from the wet lab bench all the way up to the control code.
So let's unpack this. Pillar 1 is the scale-down model. Now, usually, when I think of a scale-down model, I'm thinking of a golden batch.
Right, the ideal scenario.
Yeah, I want to create the perfect miniature replica of my best-case run. But these sources suggest doing something that sounds wrong.
It feels completely backwards at first glance. The source suggests running a 2-liter model with deliberate gradients.
Deliberate gradients. So we're intentionally breaking the process in the lab.
In a way, yeah. If you want to fix the problems in a 10,000-liter tank, you first have to understand exactly how those problems are hurting your cells.
Okay. That makes sense.
You can't just run a perfect gold standard fermentation in the lab because that doesn't reflect the reality of the plant.
The reality being that the big tank is just a really messy place.
Exactly. At scale, you have dead zones. You have these pockets where the oxygen just runs out.
Right.
You have places where the pH spikes because the base you added hasn't actually mixed in yet.
So if you only train your cells in a perfect, well-mixed 2-liter spa,
you have absolutely no idea how they'll react when they hit those rough patches at scale.
So you have to simulate the bad zones. You're effectively stress testing the biology.
We call it finding the cliff edge.
Yeah.
You need to know, how low can the oxygen go before productivity completely tanks?
Right.
Or how much pH fluctuation can these specific cells handle before they just stop making your product?
Okay.
By creating these physiological stresses in the lab, tuning the impeller speed, messing around with the gas distribution, you actually define that safe operating window.
But wait, how do you know you're simulating the right kind of bad? I mean, I could just torture cells in a blender, but that doesn't tell me anything about a production fermenter.
And that is the crucial question right there. You can't just guess. The source material really emphasizes using computational fluid dynamics, or CFD.
Math to the rescue.
Exactly. It is not just stirring slowly and hoping for the best. You use CFD to calculate these non-dimensional mixing parameters.
Like what?
Things like power input per volume, gas holdup, and circulation time.
So you actually start with the big tank.
Right. You look at the computer model of the 10,000-liter tank first. The simulation might say, hey, in the bottom third of this vessel, the shear rate is high, but the oxygen transfer is really low.
Okay.
You then take that data and tune your little 2-liter tank to match those specific physics.
It's almost like a flight simulator.
Yes.
You plug in the stormy weather data from the real world.
Yeah.
So the pilot, or I guess in this case the bacteria, experiences the exact turbulence before they actually have to fly in it.
That is a great analogy. It ensures the gradients you make are physiologically relevant.
Got it.
Because if you skip the CFD calibration, and the source is actually warned about this failure mode pretty explicitly.
Oh, well, they do.
Yeah, if you skip it, will scale up. You're just hurting cells for literally no reason.
Right, and we want actionable intelligence, not just sad cells.
Exactly.
So step one is effectively know thine enemy by recreating the enemy in the lab.
Perfect way to put it.
Once we've done that, we move to step two, which is the big tank itself, the 5,000 to 10,000 liter vessel.
And here is where we run into the problem of single-point blindness.
Yeah, that phrase really stood out to me in the reading. Most tanks really just have one sensor, right?
Typically, yes. You might have one DO probe and one pH probe, usually down near the bottom or maybe in just a convenient port.
Right.
And if that probe says DO is at 30%, you just assume the whole entire tank is at 30%.
But based on what we just said about gradients, that's practically a lie.
It is a massive assumption. Think about the volume we are talking about here. A standard probe measures a volume of liquid about the size of a grape.
A grape, really?
Maybe a large grape.
Okay, a large grape.
And you are using that grape to make operational decisions for a swimming pool.
Wow.
In a vessel that size, you have vertical stratification. The environment at the top is fundamentally different from the bottom.
So the solution kit calls for an upgrade here.
We need to see the invisible. The proposal is to install 3 to 4 DO and pH probes distributed vertically, top, middle, and bottom.
Let's talk about why the vertical aspect matters so much. Why is the top so wildly different from the bottom?
Think about gravity and pressure. At the bottom of a 10,000-liter tank, you have extremely high hydrostatic pressure.
Right, all that water weight.
Exactly. You also typically have your sparger down there releasing the gas.
So it's super bubbly down there.
Yeah, the amount of gas actively trapped in the liquid is very high. So the dissolved oxygen might actually be elevated down there just because of that physical pressure pushing the gas into solution.
Okay, so the bottom is pressurized, bubbly, oxygen-rich. What happens at the top?
As those bubbles rise, the pressure drops, the gas expands and escapes into the headspace.
Oh, I see.
So the liquid at the top might be completely oxygen-starved compared to the bottom. Or, depending on your mixing, it might actually be the other way around if the bottom is a dead zone.
But the point is, they are not the same.
They are definitely not the same.
And what about pH?
pH is even trickier. Gradients there often come from how you add things to the tank.
Yeah.
If you're dumping acid or base into the top to control the pH, it takes time to mix all the way down.
The mixing time.
Right. If your mixing time is, say, 2 minutes, you might have this cloud of extremely high pH liquid floating at the top for a long time before it finally reaches the probe at the bottom.
So the probe at the bottom says everything is fine.
While the cells at the top are essentially getting chemical burns.
Yikes. Or I imagine you could have the opposite problem, right? Something generating acid down inside the tank.
Yes, metabolic hotspots. If a cluster of cells near the bottom is growing aggressively, they're pumping out CO2 and metabolic acids. That creates a localized acidic zone that a probe up at the top would never even detect.
So by installing these 3 or 4 probes, the sources say we basically transform the reactor into a quasi-continuous spatial sensor.
I really love that phrasing. The tank stops being a black box and becomes a map. You can actually see the stratification patterns in real time. You can say, okay, the middle is happy, but the top is totally starving.
Now, I have to play devil's advocate here for a second.
Go for it.
We're talking about sterile manufacturing.
Yep.
Every single time you stick a probe into a tank, that's a hole. That's a seal.
Yeah.
That is a massive risk of contamination.
Oh, absolutely. And any production manager listening to this right now is probably sweating.
Definitely.
The sources do acknowledge this trade-off. More probes absolutely mean more complexity, more cost, and a higher risk of fouling or drift.
Right, like what if one probe goes out of whack?
Exactly. Do you trust the others? It definitely adds a layer of maintenance headache.
But the argument is that the payoff, actually knowing the truth, is worth that headache.
Because you can't fix what you can't see. If your CFD model from step 1 predicted a dead zone, these probes are literally the only way to validate that it's actually there.
Good point.
And more importantly, when we get to step 3 and actually try to fix the mixing, you need the sensors to prove the fix actually worked.
Which leads us perfectly into step 3. We've modeled the flaw. We can see the flaw. Now we have to physically fix the flow. The mechanical surgery.
This is where we get into the heavy metal, the impellers and the spargers.
The sources recommend a really specific combo here. They call for a high-efficiency hydrofoil plus a Rushton turbine. Kind of sounds like a superhero team-up.
It kind of is, honestly. In fermentation mixing, you generally have 2 competing needs, flow and shear.
Break that down for us. What's the difference?
Flow is about circulation. You need to move the bulk liquid from the bottom to the top so everything mixes together.
Okay, transportation.
Right, and that's what the hydrofoil is for. It's designed a lot like a boat propeller. It pushes liquid efficiently without beating it up too much. It creates an axial current top to bottom.
Okay, so if the hydrofoil is the transportation system, what is the Rushton for?
The Rushton turbine is the muscle. It's a radial flow impeller, usually a flat disc with vertical blades on it, and it sits right at the bottom of the tank, directly over the sparger. Its job isn't to move liquid far. Its job is to shear the gas.
Shear the gas, you mean like bring the bubbles apart?
Exactly. You want to smash big bubbles into little bubbles to increase the surface area for oxygen transfer. But Rushtons are terrible at pumping. They just spin the liquid in a circle.
Ah, so if you only had Rushtons.
You'd have great gas transfer at the bottom, but terrible circulation at the top. Pure zonal mixing.
And if you only had hydrofoils.
You'd circulate everything really well, but your bubbles would be huge. They'd just float to the surface without transferring any oxygen to the cells.
So you need both to actually eliminate the dead zones.
Right. The Rushton disperses the gas, and then the hydrofoil pumps that aerated liquid through the rest of the tank.
Synergy. Now, speaking of bubbles, the sources also talk about switching to a microbubble sparger.
That's the third piece of the mechanical puzzle. A standard sparger is basically just a pipe with holes drilled in it. It releases relatively large bubbles.
And the upgrade?
The upgrade is to use a sintered metal or ceramic frit that releases a dense cloud of microscopic bubbles.
And why is tiny so much better here?
Surface area to volume ratio. Imagine a basketball filled with air versus 1,000 tiny marbles filled with air.
Oh, the marbles have way more total surface area touching the liquid.
Correct. And surface area is where the actual oxygen transfer happens. It increases what we call the Kala, the mass transfer coefficient.
Meaning you can get better oxygenation without just blasting more and more gas into the tank.
Yes. Which saves energy, but more importantly, it really saves the cells.
How so?
Less gas flow means less foaming. Foam is an absolute nightmare in fermentation.
Right, it traps things.
It traps cells, it wets the exhaust filters, and it requires you to pump in anti-foam chemicals, which can eventually clog up your downstream purification membranes.
So the microbubbles keep things a lot calmer.
Exactly. And less violent turbulence is just generally better for the cells, although we should definitely mention the risks.
There are always risks with these things.
Always. The main one here is shear damage.
From the impellers.
Yeah, even though the hydrofoil is gentle, that Rushton turbine at the bottom is very aggressive.
Right, the muscle.
Plus, sometimes microbubbles can actually create very stable foams that are incredibly hard to break. If you overmix to try and get that perfect homogeneity, you might physically beat the cells to death.
Oh, wow.
It's a delicate balance.
So we've rebuilt the engine. We have the hydrofoil Rushton combo. We've got the microbubbles, and we have the spatial sensors watching everything. Now we just need a driver.
Yes.
This brings us to Pillar 4, Advanced Control Strategies.
This is where we close the loop. The hardware gives you the potential for homogeneity. but the software ensures you actually maintain it.
And the sources detail two specific strategies here: DUSAT exponential feed and pH cascade control. Let's take those one by one.
Sure.
Diostat exponential feed. That sounds a little complicated.
It's actually quite elegant once you see it in action. In a fed batch culture, you're constantly feeding the cells glucose or some nutrient source over time. Usually you just follow a preset recipe. Feed X amount at hour Y.
But biology doesn't always read the recipe book.
Exactly. Sometimes the cells grow faster, sometimes they grow slower. Duostat control actually listens to the oxygen levels. It exploits the fact that eating requires breathing.
Okay, walk me through how that works practically.
When cells consume a nutrient, they have to consume oxygen to burn it. If the DO level in the tank starts to suddenly rise, it means the cells have stopped eating.
Because they've run out of food and stopped breathing as hard.
Exactly. So the system sees the DO go up and basically thinks, dinner time.
And it automatically triggers a feed.
Yes, but it's not just a simple on-off switch. It uses an exponential algorithm to match the specific growth rate of the cells.
Okay.
It aims to keep the cells in a constant, happy metabolic state.
So instead of just force-feeding them on a schedule, the tank is responding to their actual appetite in real time.
Precisely. It stabilizes the metabolism. If you prevent the cells from starving or overeating, you prevent those metabolic spikes.
Like the hotspots we mentioned earlier.
Yes, the very hot spots that cause the gradients in the first place.
That is so cool. And then we have pH cascade control. How does that differ from just trying to keep the pH stable normally?
It goes right back to our multi-probe setup. Standard control just looks at one single probe. It says pH is low, add base.
Right.
Cascade control looks at the spatial data from the top, middle, and bottom simultaneously.
So if the bottom probe sees an acid spike, but the top probe says everything is totally fine.
The system is smart enough to interpret that discrepancy. It cascades the decision. It might actually just adjust the mixing speed momentarily to blend that acid spike away.
Instead of just dumping in more chemical base.
Exactly. Because if it dumped base based on the bottom probe, it might fix the bottom but make the top way too alkaline.
It verifies the action against the mixing time to ensure it doesn't overshoot.
It acts locally to fix global problems.
It turns the whole system from something static into something truly dynamic. It actively fights the formation of these microenvironments.
It does. But again, the sources do warn about tuning.
Tuning the software.
Yeah, the PID loops. Proportional, integral, derivative. You have to perfectly tune the gain, the deadband, and the response time.
And if you don't,
If you get the parameters wrong, the system can oscillate.
like a yo-yo effect.
Exactly like a yo-yo. The pH drops a tiny bit, the system panics and dumps base, then the pH shoots up too high, so the system dumps acid.
Oh, man.
The controller basically freaks out, and that is so much worse than doing nothing at all, because you are heavily stressing the cells with these constant violent swings.
So you really need to know what you're doing.
Yeah.
This isn't just a plug-and-play app.
It requires deep expertise. But when it works, you have a tank that is essentially self-correcting.
Okay, so let's synthesize this whole 7 to 10 day sprint. Day 1 and 2, you build a bad scale-down model using CFD to find the cliff edge.
Yeah.
Days 3 to 5, you retrofit the big tank with vertical probes to actually see reality.
Yep.
Days 6 to 8, you install the hydrofoil, Rushton, and microbubble hardware to fix the flow. And finally, you implement the smart control loops to keep it all stable.
It is a complete workflow. Model the flaw, see the flaw, mechanically fix the flow, and regulate the stability.
And the end result for the listener, like, why should they care about doing all of this intensive work? Why not just accept the scale-up paradox like we always have?
Because uniformity equals robustness. If you have gradients, you effectively have 3 or 4 entirely different fermentations happening inside the exact same tank.
Right.
Some cells are perfectly happy, some are starving, some are suffocating.
And those unhappy ones aren't just, lazy.
No, they're active sabotage agents. Stressed cells often lyse, meaning they pop open.
Okay.
And when they pop, they release proteases,
What?
enzymes that literally chew up proteins. So the dying cells are actively destroying the valuable product that the living cells just made.
That's a wildly vivid image.
Yeah.
So by eliminating the gradients, every single cell becomes a productive, protected worker.
Exactly. And that is exactly where that 18 to 25% titer increase comes from in the E. coli case study.
It's not magic.
Not at all. It's just ruthless efficiency. And honestly, more importantly, it gives you reproducible batches.
Right. Less variation.
You don't have to cross your fingers and just hope the mix works this time. You know it will, because you are actively controlling the microenvironment.
It really takes the art out of fermentation and puts the rigorous engineering back in.
Which is exactly where it belongs in commercial manufacturing.
Well, here's where it gets really interesting to me.
Okay.
If we can see and control these environments so precisely now, using the CFD, the spatial sensors, the smart loops, are we approaching a point where the scale-up effect just sort of disappears?
Now that is the provocative thought. For decades, we have just accepted that scale-up means loss.
Right, the biology tax.
Exactly. We literally build in safety margins, assuming we will lose 20% of our productivity when we finally go to manufacturing. It's treated like a tax you just have to pay to physics.
But if we can truly, perfectly homogenize a 10,000-liter tank,
If we can make the 10,000-liter tank mathematically and physically identical to the 2-liter benchtop, then maybe the era of the scale-up factor is ending.
wow,
Maybe very soon, what you see in the lab is exactly what you get in the plant, every single time.
a world where the biology honestly doesn't even know how big the tank is.
It would change the economics of absolutely everything from life-saving pharmaceuticals to industrial enzymes.
It would be a total paradigm shift.
We aren't quite there yet. For everyone, it takes a lot of work, capital, and expertise. But this specific solution kit is a massive, massive step in that exact direction.
Well, there you have it. From deliberate gradients to microbubbles, a true masterclass in taming the giant tank. Thanks for diving in with us today.
Always a pleasure to be here.
This has been The Deep Dive. Catch you next time.
That concludes today's challenge and its implementation pathway. In the next episode, we break down another real-world fermentation constraint with clear actions and measurable outcomes. Stay tuned to biomanufacturing and fermentation technology, where process science turns into engineered performance.